Hello, welcome back. Today we are discussing limits from section 1.5. The learning objective for this video number 2 is to compute limits using a variety of techniques. So we're going to start with the list of properties, because you liked them so much last time, I'm sure, that we looked at the end of video 1, just to remember how little we liked this. So I want to reiterate that I'm not expecting anybody to get much out of this page right now. I think it's not until we actually do a couple of examples that this feels at all like something that might be worthwhile. But the upshot was there are these properties of limits. They help us break up functions over addition and subtraction so that we get smaller pieces and ideally, if I'll go back one more slide, give us these two helpful limits to actually work with. Because it turns out a surprising amount of the time our limits reduce to either x or some constant, and then we can apply all these properties to it. So let's see how that works. So evaluate the limit just using these properties of limits and the two earlier ones that we developed. So there's our limit expression. We're getting really fancy here. T is our input instead of x's, but that's the same as x, just a different variable name. So t approaches -1. We'd like to know what happens to this limit. So maybe for perspective, the first thing we did in video 1 was to visit this from the possibility of, from the perspective of using numerical evaluation. That is, choosing some number values for t that are close to -1 and then make some kind of guess about where this is headed. As you can imagine, in general, if you use the word guess in mathematics, that's probably not a strategy that's going to stick around for forever. So while that's a good initial approach, we're going to try to find some better ways to tackle this. That said, there are some really good circumstances where your time is best spent just trying to get some numerical values and have a good educated guess about the value of this limit. Okay, so basically the notion is that we're going to break this expression up. We're going to take what is currently one big expression separated by some addition and subtraction and use those properties of limits to break things up. So, for example, we've got subtraction and addition, and basically our limit properties from before, although it's very hard to tell that just from looking at them, but what their statements basically say are that if you've got, in this case, t to the fourth and you're subtracting t, and they're all inside this one limit, well, you might as well just break that up into limit of t to the fourth minus limit of t. Of course, they're still going to the same place. Still t is going to -1. So the subtraction lets us break these two pieces inside up into two broader pieces. And then if we do this again for the addition that's part of this problem, we're adding 1 over here. So these limit properties say, okay, well, if you're taking, I guess it's -t, but after the subtraction, if you're taking t and then adding 1, you can write that as a limit of t and then plus limit of 1 all by itself. And then there's actually one additional thing that happened here. This would look like limit of t to the fourth just by itself. So forget about that for a sec. But one final property of limits we can employ here says if you've got your variable, and it's really any function inside here, but t in particular, and it's being raised to a power, you could just bump that power outside of the limit. So now it's just limit as t goes to -1 of t, and that fourth power is on the outside. Okay, so some perspective is in order here, because why would we want to do this monstrosity of effort that we just put forward? And here's the reason. The things that we have left now are limit of just our variable by itself, limit of just our variable by itself, limit of some constant. And if you recall, those simple limits we were given a couple of slides ago perfectly tackle these scenarios. They tell us exactly how to get limit of just t, or x as it was originally stated, but so limit of just t by itself, limit of some constant, those are very easy for us to put together. As t approaches -1, t approaches -1, it turns out. So we've got our the result of this inside these big parentheses here is -1, because surely as t approaches -1, we could say that t just by itself also approaches -1. And that happens again here. We're still subtracting, so let's keep track of the signs that are occurring here. But limit as t approaches -1 of t is still -1 again. So we're just taking these simple limits, pushing everything away, subtraction, addition, exponents, all that stuff, until we get down to just those handy limits that we were handed. And then finally, we're supposed to add whatever the limit as t approaches -1 of 1. Well, this has no t's in it. This has none of our variable stuff in it. So it doesn't matter what t goes to. 1 is going to stay 1. So there it is. And now we've taken this horrifying expression with limits in it and turned it into something with just numerical values. But -1⁴ is 1. This is actually plus 1 more, and then plus yet 1 more gives us a grand total of 3. So it turns out that for certain types of functions, in particular rational functions, we can do this with regularity. We could always break these things up into nice pieces. And what we really conclude from this is that if you have any rational function, if you look at the limit as x goes to some number, or t like it was a minute ago, and you ask what is the value, what is the limit of this rational function as x approaches a, it's just what you get with a plugged in. So let me say that again. The limit as x goes to a is just this thing, this whatever sort of fraction or polynomial thing you had, is the whole limit is just take the expression and plug in the number that's down here. And this is true, and this is an important catch, that it's true as long as you don't get to say division by 0 or well, 10 over 0, 0 over 0, some sort of indeterminate form like that. So as long as r of a is actually a real number, then this will always be the case. So limits are not really all that fancy. If what you're looking at is either a polynomial or just two polynomials divided. That's all a rational function really is. So if you have a polynomial, that really is a special kind of rational function. It's just one where you're not really dividing by anything interesting. You're dividing by 1. And so the theorem applies to the example we just did. But we'll try one additional one just to kind of get the notion of what's going on here. So this says we're trying to compute what looks like fairly complicated limit as x goes to 1. And then we have on top we've got x cubed plus 1, on bottom is x squared plus 2. And each of these things is a polynomial. They look like x to some whole number, some positive whole number power. And so this must be a rational function. And so we could go through all the rigmarole of what we did for that last example. We could break these things up over division and addition and over the powers and then look at these limits as just x goes to 1 of x. But what this theorem does for us is pretty nice as long as this is defined at x equals 1. So that's the first thing to check. So if we look at x equals 1, really the only thing that could go wrong is that we would divide by 0 by some accident. So if we plug in 1 for x, 1 squared is 1, plus 2, we're dividing by 3. That's actually not a problem at all. Division by 3 is great. So what that means is instead of going through all those big properties, we can just use this nice theorem, which says you have a rational function, you have a limiting value at which the function is defined. So go ahead, get rid of the limit symbols, and dump in 1. The limit is equal to what this expression looks like at x equals 1. So we replace all the x's with 1s, we get rid of the limit expression, the limit kind of operator really out in front, and then our conclusion is, well, 1 plus 1 over 1 plus 2, so 2/3. So without having to go through all those properties, which really this theorem is just operating under the hood. All those properties are feeding this, this particular type of function that we're trying to evaluate. So we get a fairly concise answer out of this. The limit as x approaches 1 of that fraction-y thing is 2/3. We'll do one more of these with an applied context. So we have competing companies. We've got profit functions for one of them, x squared minus 4. Profit function for the other is x squared plus x minus 6. And then just to keep track of units, x thousand units are sold. And then we're asked to notice that each of these companies has a break-even point when they sell 2,000 units. Well, keep in mind that 2,000 units really means that x is equal to 2. But if we took x equals 2 and dumped it in here, we would get 2 squared, which is 4 minus 4. That's a profit of 0. And that's what it means to have a break-even point at that production level. So profit of 0 for the first company. If we plug in 2 here for the second company's profit, we get 2 squared is 4, plus another 2 is 6, and then minus 6 we get 0. So each of these has a break-even point at 2,000 units sales. And then the real question is, what is the ratio of these profits for the companies when sales gets close to this break-even point? So so much of math is just translation, but when we say, okay, we approach the break-even point, just remember that they already told us the break-even point is, mathematically, x equals 2. So we could just replace this, the break-even point, with the statement x equals 2. And again, so much of math is substituting these things, and especially applied problems, where we take words in English and turn them into mathematical statements. Okay, so we want ratio of profit. Ratio, if you recall, is division of these two things. So what we really want to do is take a look at profit 1 and divide by profit 2. So this is mathematical notation coming to the fore again. What we really want is an approach. So if you recall, approach is a keyword for limiting behavior of some sort going on here. So we're trying to approach x equals 2, and we're looking at the ratio of these two profits as we do that. So this first step is just replacing profit 1 on top with its actual formula and profit 2 on bottom with its formula. So what would be fantastic, and is a worthwhile thing to notice, is that if this theorem about rational functions could work for us, it would be a huge time saver. It would mean that we could just take 2 and dump it into the top and the bottom. And this is a rational function. It's got a polynomial on top and a polynomial on bottom. That's all a rational function is. However, if you notice, if we actually plug in 2, like we did informally a minute ago, profit was 0 for the first function, it was also 0 for the second function. 0 over 0 is not a very helpful number to work with. It's not clear exactly what that's trying to tell us. So more specifically, it's not a real number. Okay, so our theorem does not apply, and then we actually have to go through some kind of process to simplify here. So one nice thing that this suggests is when you get 0 over 0 from this limit, this is called an indeterminate form, but that's not terminology you have to be responsible for right now. That tells us that maybe some simplification would actually help us out. So if we take x minus 2, and we'll go through this more slowly than this is showing, but x minus 2 is a factor of these two things on top and bottom. X squared minus 4 can be broken up into x minus 2 and x plus 2. So that's a convenient factorization. And then on bottom, we've got not an identical factorization, but a similar factor between them, which is actually just as good. So here is profit function number 2. That, with some convenient factoring, looks like x minus 2 times x plus 3. And then the great part about that, of course, when you have a factor common on top and bottom, that factor can be removed. So with that factor gone, all that's left is this x plus 2 over x plus 3. And we're going to show ourselves that here just to remind it. So again, these two factors cancel. We've got this expression left over. Now, let's revisit this. If we take a look at this and think once again about our rational function theorem, the thing that lets us just basically plug in this number, assuming that it's not undefined. As at x equals 2, this would have a non-zero number on top, but more importantly, it would have 5, a non-zero number on bottom. So actually, our limit for rational functions applies in this case. It means we get to say that the limit of all this expression is the exact same thing as what we would get if we just dumped in 2. So if we plug in 2 top and bottom, we get ourselves 4/5 or 0.8. That's a good mathematical conclusion, but to be perfectly polite, we should return to words before we're done. So in other words, since we took profit for company 1 on top and divided by profit for company 2 on bottom, we would say that as we approach this break-even point, the 2,000 unit mark, then sales for company 1 is about 80%. It's approaching 80% of the sales for company 2. That's actually a sort of interesting conclusion, given the fact that we had 0 over 0. So when somebody asks you, what is 0 over 0? You can say, well, depends, but in this case, it's 0.8 somehow. The beauty of math. So that's it for Learning Objective 2 in section 1.5. I'll talk to you soon about our final learning objective for this section.